now we understand the reason why there's 4 equivalent bonds or bond positions, because instead of having 1 s orbital and 3 p orbitals, we now have 4 of these hybrid orbitals. Now, because we used an s and we used 3 p orbitals, I'm going to write that, oops, not like that, that's nothing. I'm going to write that this way, right? We used 3 p orbitals. I'm going to write them separately just so you don't think that it's 3p versus 2p or 4p. Right? But we used 1 s orbital and 3 p orbitals. And what we end up with are 4 sp3 orbitals. And we represent that as sp, and p is has a superscript 3. And so that's 1s and 3p orbitals. Okay. I'm gonna use words instead of numbers again, just so you don't think that I'm talking about shells. It's a single s orbital and 3 p orbitals that we hybridize together to get these new sp3 orbitals. And so we get 4 of them. Maybe I should write a little. We get 4 sp3 orbitals. All right, and so the number of hybrid orbitals, which is 4 in this case, equal the number of pure atomic orbitals, 1s plus 3p. Oops. 3p. And so we get 4 hybrid orbitals from our 4 atomic orbitals. Once they've hybridized, they point to the points in space. They reorient themselves to the points in space where those regions of electron density are the farthest apart. Okay. And so then how hybrid orbitals work is that whenever we form a covalent bond, remember covalent is sharing electrons, the only way to form a covalent bond is either an overlap between, it can be atomic orbitals and atomic orbitals, but that's only in very simple cases where let's say it's HCl or something, right? It's only a diatomic molecule. Generally speaking, it's an overlap of some hybrid orbital, either with an atomic orbital, if it's just a single bond, or it can be with other hybrid orbitals. And so here in carbon, you can see in blue, we've got our sp3 hybrid orbitals. And they're overlapping with the 1s orbital for hydrogen. Remember, hydrogen only has electrons in the 1s orbital, and so he doesn't really have any other orbitals that he can hybridize. Okay. The other thing to point out about hybridization is that it only occurs within the same shell, right? And so we can't hybridize some 2s orbitals with some 2p orbitals. That's okay. But we can't do 2s and 3p, right? They have to stay within the same shell. And so that's why hydrogen doesn't hybridize with the 2p orbitals, because he doesn't have, we can't get that sort of cross shell hybridization going on. And so just as a recap of covalent bonding, this region here where there's overlap, that's what we sort of consider that covalent bond, right? That's that connection, that's that sharing between carbon and hydrogen. We draw it like this, but hopefully we know by now that it's there's much more overlap than that. This is just an artist's rendition. Okay. All right. And so those are sp3 orbitals, and that's again 1s with 3p orbitals. If we look at the hybridization in ammonia, again, it's sp3. Not that nitrogen atom has 1 2s orbital and 3 2p orbitals. Those all hybridize. We end up with this lone pair in its orbital at the top, right? That's the way that we talked about it when we went through that those molecular geometries. But this hybridization predicts this correct bond angle, right? This bond angle that's about 110 degrees. Okay. If we didn't think about it in terms of hybridization, we would say that that lone pair, you know, if the orbitals didn't hybridize, then that lone pair would just be in a random atomic orbital and wouldn't really contribute to the geometry at all. And with hybridization, we see that it does. And so hybridization ties in very well with this VSEPR theory of molecular geometry. Okay. All right, so there are other types of hybridization, right? Because of course there are other geometries. And so when we look at, if we think about the hybridization, if there are around a central atom, right? If there are a total number, there are a total of 2 lone pairs and bonded atoms. Let's make another column here. What's that molecular geometry? We have 2 lone pairs / bonded atoms. What did we call that?
Bent.
So that would be if it was 2 lone pairs and 2 bonded atoms, but just a total of 2. If I'm just bonded to 2 things, it's got to be
Linear.
Linear for sure. Okay. And so if I'm linear and I only am bonded to 2 things, or I have a bond and a lone pair, then do I need to hybridize all 4 of those orbitals? No, I don't. I only need to hybridize enough orbitals that I can fit everything I want to bond to. Right? And so if I'm only bonding 2 orbitals, do you think it's going to be an S and a P or just 2 P's?
It's P.
Yeah, it's going to be an S and a P. Remember, one of our first rules of hybridization, that the 2 orbitals have to be different types of orbitals. And so we can't get just some P hybridization going on. And so that hybridization is 1s and 1p. And so we just call it sp hybrid. A good example would be our beryllium chloride, which was our example for the exception to the octet rule that only had 4 electrons. Okay. If we go up to 3 lone pairs or bonded atoms, what was our molecular geometry?
Trigonal planar.
That's it, trigonal planar. Now I'm adding in another orbital, and so we're up to sp2. And again, one of our examples for this was bf3, which was one of those low electron exceptions for the octet rule. But this is also where the formaldehyde that we talked about earlier, the CH2O, with the 2 bonded hydrogens and then a double bonded oxygen, that also fits in sp2. We'll come back and talk about that one in a minute. So if we have 4 bonded atoms, then what's our shape? We've already talked about this one.
Tetrahedral.
Tetrahedral. And like I said, we've talked about this one. We know that it's sp3, and so, you know, anything works as a good example for tetrahedral. When we go up to 5 lone pairs and bonded atoms, what do we call that geometry? I should say, maybe this was confusing earlier. I should say this is our electronic geometry, if it's a mix of lone pairs and bonded atoms. But if we have 5, what shape is that?
Trigonal bipyramidal.
That's it. Now we have 5 bonded atoms. Now that's how many electrons if we have 5 bonded atoms?
10.
10. So we said that, things that have more than 8 electrons that break that octet rule, that have that expanded octet, where do they get there? Where do they put those extra electrons? In the D subshell, someone said. And so instead of just having 1 s and 3 p's, we're going to throw in a d orbital as well. So now we're at sp3d, right? And I think the one that we drew was PCl5. But that shows you, that hybridization shows you where that extra d orbital, how it comes into play. And then, of course, the last one with 6 lone pairs or bonded atoms. What do we call that guy?
Octahedral.
Octahedral. And who wants to take a stab at his hybridization?
sp3d2.
sp3d2. That's right. We just need 1 more orbital to fit that extra pair of electrons. And SF6 was our example for octahedral. Okay. And so knowing this electronic geometry will help you know the hybridization required. So if we can draw a Lewis structure and we can figure out the electronic geometry, right, then we can figure out what the hybridization should be for that molecule. All right, so let's do an example. Determine the hybridization state of the central atom in each of the following. I got rid of the big ones that had more than 1 central atom, and so that underline doesn't really make a lot of sense anymore, but there we go. And so, to do this the right way, we should draw some Lewis structures. Beryllium dihydride, that's this first one. Beryllium has 2 valence, each hydrogen has 1, so it's a total of 4 valence. Well, there we go, that's it. What's the geometry of this?
Linear.
Linear, and so what's the hybridization?
sp.
P. How about ALI3? I won't draw it out, but what did you get for the hybridization of aluminum triiodide?
sp2.
sp2, that's right. Aluminum, and I remember aluminum is one of those metalloids. He most of the time behaves like a metal. Every once in a while, especially with these less electronegative elements like iodine, he will behave like a nonmetal. And so he doesn't have that extra lone pair. He only has 6 valence electrons. And so he's sp2. pf3.
Is it also sp2?
It is not sp2 because that phosphorus, unlike aluminum, does have an extra pair of electrons. He does have a lone pair.
So sp3.
That's it, sp3, because pf3 has a lone pair. So we have to count that lone pair when we look for the electronic geometry, and that gives us hybridization. All right. So phosphorus and phosphorus pentabromide. I gave you phosphorus pentachloride as a good example of one of our hybridizations. All right. He doesn't have any lone pairs, and so it's just the same as his molecular geometry. What hybridization is necessary for phosphorus pentabromide?
sp3d.
sp3d. So we just count up, essentially we're counting up the number of bonded atoms and the number of lone pairs on that central atom, and we need that number of orbitals. We're going to start with the s, we're going to add in up to 3 p's, right? And then we're going to jump in with the d's if we can't cover it. Okay. All right. Oops. So when we do this hybridization, what happens is that the energy levels are essentially evened out between the s orbitals and the p orbitals. So they draw them in boxes. I'm just going to draw them in lines, but we know that the 2p orbitals are a little bit higher in energy than the 2s orbitals. When we look at carbon, carbon ends up like this. Now, if we were going to hybridize carbon, he's got 4 electrons. If we're going to hybridize carbon into an sp3 state, it's pretty easy to see. I'll do that first. We're going to end up with 4 orbitals, 2sp3, that are all the same energy. And that's where we would get the 4 different bonding groups on carbon. However, this is for sp3 hybridization. Since this slide talks about sp2 hybridization, again, it draws it out over here in the boxes, but I'm going to draw it out in these sort of the appropriate energy levels. Again, we start with 2 s's and 2 in the p's. Now, if we only hybridize and we need sp2 hybridization, so that leaves 1 electron that's not hybridized, well, we end up with 2 sp2 hybrid orbitals, and then this leftover 2p. And so the way that the hybridization process works is that those electrons are still spread out even into those unhybridized orbitals. And so we don't go back and form a lone pair when we have an unhybridized orbital in the same energy level. And so this is what we end up with. Again, that is exactly what they're showing here. We have the sp2 orbitals here, and then this last electron is in the p orbital that's unhybridized. But he doesn't, he still gets to keep an electron. It's not that the electrons are all shifted away. And so what we end up with is we end up with a carbon that is going to end up bonded to 3 different atoms, right? Because he's sp2 hybridized, we know that he's going to make 3 bonds. But then what in the world does this little leftover 2p electron do? Well, it turns out that when we when we look at the hybrid orbitals, we have those hybrid orbitals in green. Those are sp2 hybrid orbitals. And then that unhybridized p orbital is left over, and that's in gray. And so remember, each one of these has a single electron in it right now before we make any bonds. And so I told you we'd come back and talk about formaldehyde. Well, what formaldehyde does is that there's hydrogen. Hydrogen comes in and bonds with carbon. Another hydrogen comes in and bonds with carbon. And then oxygen comes in. Now, oxygen, it turns out, is also sp2 hybridized. And so he's going to have his hybrid orbital. I'm going to draw it this way. He's got a hybrid orbital here. And he's got other hybrid orbitals. Oof. And his other hybrid orbitals, well, let me actually draw this Lewis structure real quick. So we end up with hydrogen, hydrogen, oxygen, like that. That's the Lewis structure for formaldehyde. We did that several class meetings ago. But he's also sp2 hybridized because he's bonded to one atom and he's got 2 lone pairs. And so he ends up with the same sp2 hybrid orbitals. And so we get this overlap for one of the bonds. And then this hybrid orbital has a lone pair. That hybrid orbital has a lone pair. And there's an electron in his unhybridized p orbital. There's an electron in carbon's unhybridized p orbital. And what happens is that extra electron that's unhybridized forms another bond, right? So these 2 regions overlap and form a second bond. So in black here, right, bond 1 is in black. Well, I'll come back to this in a minute, but we call that a sigma bond. And bond 2 is in blue. Right? And so, yes, that's 2 different places where those orbitals overlap, but those 2 different places are still just that one orbital, that p orbital on both atoms that overlaps. And so that overlapping orbital gives us another bond. We call that a pi bond. Sigma for s orbitals overlapping, pi for p orbitals overlapping. Anybody want to take a guess what we do if there are d orbitals that overlap?
Delta.
Delta, you bet. Yeah. And so delta bonds are really uncommon, except in things like heavy metals. So we will not talk about them very much, but yeah, this is what it looks like when we have unpaired electrons that in unhybridized orbitals. They're likely to form some double or triple bonds. Okay. So let's look at an artist rendering that's probably a little bit better than mine. So this is ethylene, C2H4. If we draw the Lewis structure, CCHHH, that's 10 electrons. I should have a total of 12, 4 and 4, and 4 times 1. So I should have a total of 12 electrons. That's 10. If I put my lone pair on this carbon, then the other carbon doesn't have enough, which means I need a double bond. And so this is my geometry. Each carbon is trigonal planar. So each carbon should be sp2 hybridized. And so that's what they've shown here, right? These are in green. These are sp2 hybrid orbitals. And we have some bonding here. So this is a sigma bond between carbon and hydrogen. This is a sigma bond between carbon and hydrogen. This is a sigma bond between carbon and hydrogen. This is a sigma bond between carbon and hydrogen. This is a sigma bond between carbon and carbon. And so they're just showing what's in the plane in this diagram in A, right? Now that we have all of those, so just so you know, right, there's a hydrogen here and a hydrogen here and a hydrogen here. They're not showing the hybrid orbitals in this second frame. Right? They're just showing those p orbitals. And so those p orbitals, right, these are unhybridized. And we're going to call that a pi or a pi bond. Now, I don't write pi in both places because it's easy to get confused and say, oh, that's two pi bonds. Pi bonds have overlap in two regions, above and below the plane of the molecule or the plane of the bond, because that's just the shape of a p orbital, right? The p orbital has that sort of double lobe shape. And so when p orbitals overlap, they overlap above and below the plane of those molecules. And so that's a pi bond. And when we look at all the orbitals here put together, we have a sigma bond between carbon and hydrogen, sigma bond, sigma bond, sigma bond, 4 sigma bonds between carbon and hydrogen. And then this double bond is 1 sigma bond and 1 pi bond. Again, I just want to be clear that that pi in the bottom isn't a separate pi bond, right? It's just those two regions of overlap. Okay. So a single bond is just 1 sigma. Obviously, we see that between the carbon and the hydrogen. A double bond is 1 sigma and 1 pi. Right? A triple bond, who wants to take a guess?
Is it 1 sigma, 1 pi, and 1 delta?
Yeah, it's not delta yet. Like I said, we won't really get into deltas. And so we're only going to have 1 sigma between two atoms ever. And so we have 1 pi for double, and we have another pi if it's triple. And so a single bond, oops, let me get out of yellow because you'll never see that. A single bond is just 1 sigma. A double is 1 sigma and 1 pi. And then a triple, instead of adding a delta, which I admit is maybe the progression that makes more sense, but we end up with 2 pi's. And let me quickly show you why. If we have a triple bond, let's say it's a simple triple bonded molecule like carbon monoxide. If I choose the carbon to be the central atom, how many hybrid orbitals does carbon need? He's only bonded to 1 atom and he's got 1 lone pair. So how many hybrid orbitals does he need?
Two.
Is it 1?
Just 2. So he needs 1 for the bond and 1 for the lone pair, right? And so for carbon, oops, right, again, he starts this way. It's a real bad arrow. He starts this way, 2s and 2p. When he hybridizes to form the 2 hybrid orbitals he needs, that's 2sp. Then he's left over with some 2p's. So there we go. Everybody gets an electron. It's like Oprah. And so we have our hybrid orbitals for the lone pair and for the single bond, the sigma bond. And then we've got 2 p orbitals left over for the pi bond, right? And so this is going to be for a sigma. This is going to be for our lone pair. And this is going to be for a pi bond and another pi bond. Okay. So that's why it doesn't jump up to delta just quite yet. If we had to make more than 4 bonds, that's when we jump to delta bonds, right? If we can do 4, then it's just going to be sigma and pi. When we have to make more than 4 bonds, that's when we start worrying about those delta bonds. Okay. So this is what I just drew on the other screen, but you can see that you have these 2 unhybridized p orbitals. The textbook has colored these the same color, which makes sense because they are both pi orbitals. But I'm going to color one of the pairs just a little bit darker. I hope that that's different on your screen, because maybe you'd think that you know, these 2 that are on top of the purple bond, those are a pair, and then the 2 on the bottom are a pair, but that's not how it works. Remember, p orbitals are opposite one another, and so that the p orbital that's on top is actually paired up with this p that's on the bottom, right? So remember, the p orbitals are above and below the atom, and so if I were to draw in the p orbital, you know, it would look like this. That's no bueno. You'd have one that looked like that for top and bottom, and then you'd have another that looked like that for left and right, right? And so that's where that overlap comes from. So you have these 2 pi bonds. One of them has an area of overlap that's above and below, and the other one has an area of overlap that's left and right. This is C2H2, by the way. So we've done formaldehyde already. But just for a brief refresher, this bond is what kind of bond?
Sigma.
Sigma. This bond is what kind of bond?
Sigma.
Sigma. Now, can I tell whether the one on the bottom or the one on the top is sigma versus pi? No, I can't tell. So you just have to tell me that this double bond is what?
1 sigma and 1 pi.
That's right. Sigma and pi together. Okay. All right. Okay. And so that is hybridization. And sort of what hybridization gives us is not only the sort of the mechanism for those orbitals to spread out in the directions they do, but also it helps us think about why double bonded molecules are able to take on those same predicted geometries from VSEPR theory. And it has to do with the fact that those hybrid orbitals separate themselves as much as possible in space, and then those unhybridized orbitals, they also, you know, try to get as far apart as possible, but they are able to participate in double bonding and triple bonding. Okay. Are there any questions about hybridization? I know that was maybe a lot, or quickly. All right. Well, if there are no questions, I'm going to leave it there. The tail end of chapter 10 is all about molecular orbital theory. And we will come back and do that on Monday after the break. I hope that you have a good Thanksgiving and enjoy some time safely with people that you care about.
Thank you.
Yep.
Davis, happy Thanksgiving.
Bye.
Happy Thanksgiving.